Okay, guys. So this is a chapter 2 review. This is probably a little more difficult than chapter 1 review. So it's probably important you watch this video. It's on topics such as the least squares regression line, residual plots, and association and causation. Many of us sort of didn't really have a full understanding of least squares regression lines in our assignment. And for your exam, I can safely say that you should expect questions on least squares regression equations in your exam, and this video walks you through how to do some of those questions. So I would suggest watching. So the first one is the least squares regression line. So fitting a linear model to numerical data. So once we identify there's a linear association between two variables, we can fit a linear model to the data and find its equation. This equation gives us a better understanding of the nature of the relationship between the two variables, and we can also use the model to make predictions. This process of modeling an association with a straight line is known as linear regression, and it's often called the regression line. So here is an example. Here we have graph in Excel or a scatter plot of saying, can arm span predict height? Okay, actually that's wrong. The scatter plot should say, does distance from the CBD impact house price? Okay, and so when we look at this example, this is like what you did in your assignment. Here we look at that, and I think it's clear that we could put a line through this because it looks like this has quite a strong correlation. So does it look like there's an association? Yes. Okay, therefore we can fit a regression line to our data. We did this in Excel for your PSMT, and you can see it there. However, the above line actually has a name. So you should know that any line on a graph can be called like something x plus something, okay, y equals something x plus something, or there's loads of different names for different lines, for straight lines on a graph. Okay, so how do we name this line? So we'll have a look at an example. Okay, so to calculate the least squares regression, okay, so to determine the equation of that line, so what is the name of that line, that's what that means, you need to be able to determine the values of the intercept A and the slope, which is B. So this is the formula, y equals a plus bx, okay? So to determine a and b, we can use these formulas. So b is the r, which is the correlation coefficient, multiplied by the standard deviation of the y's over standard deviation of the x. And then a equals the mean of the average of the y's, take away b times the mean of the x. A lot of information. We'll look at these two examples. So we'll look at this example first, and if you were asked to do this in the exam, they would give you all of these values. They would give you R, they would give you this, 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 and then you need to go and work out what is B, what is A, and can you then put those two values into this, okay? So we'll look at that first, and then the second one we'll look at is finding the A and B. We can find them in our calculator like I showed you before. Okay, so let's look at example 1. Okay, example 1, you should probably do the working out of this question in your book as well. Okay, so the height X and the weight Y of 11 people have been recorded and the values are determined. So here's an example where they've actually already worked out what the X mean is, what the standard deviation of the X's are, the Y mean, the standard deviation of the Y, and the correlation coefficient. So now we're going to use the formula from the previous page to determine the least squares regression equation. So first step is, if we go back, we start with B. And the reason we start with B is because we actually need B in here to work out A. So we can't possibly work out A unless we find B first. So B's formula is here. Okay, we go and sub in the values. So R, 0.8502, sub in, multiplied by, because it's next to, anytime letters are next to each other, it means times. So multiplied by standard deviation of Y, which is this. Okay, divided by the standard deviation of X, which is this. Put that in our calculator to 2 decimal places. We get this as our answer. Okay, next, we're going to calculate the intercept. So for the intercept, we're going to use this value here, 65.45. We sub it in. subtract, we go and put B, which we just worked out as 0.87, so say 0.87, and we're multiplying that by the mean of the x's, which is 173.3. That gives us this figure. Now we've got our B, now we've got our A, we can go and put that into the least squares regression equation. So that's what it looks like, y equals A plus BX. We go and put A, so 85.32. We go and put that here. I'll probably add that in, 0.32. So 85.32 plus B, which is over here, 0.87. Okay, and then that still needs to be multiplied by X on the other side. So I'll just put 32 here. And then the last thing that you do is once you've got the least squares regression equation, you need to make it make sense. So with your PSMTs, you should have actually written like house price equals this plus this multiplied by distance from the CBD or whatever you did. For this question, we go back up and it says that height was X. So that means that X value we have to change with the word height, and Y was weight, and we changed the Y with weight. So now we actually have an equation. Your weight is going to equal negative 85.32 plus 0.87 times your height. So if we knew what someone's height was, if it was, say, I don't know, 165 centimeters, we can put that in here and put that in our calculator and approximate what their weight would be. We can also actually approximate what someone's weight is. So, someone's height is. So if we knew that someone's height, if we knew someone's weight was, say, 70 kilos, we could say 70 equals negative 85.32 plus 0.87 times height, and then we have to start moving things around and solving using inverse relations to find that answer, okay? And that's on predicting, which we'll show you shortly. So that's all you have to do. You have to just find B, A, and then write down the equation. The second example is doing this on a calculator. So these dirt bikes that we listed before, you can just go back, put them all into your calculator, and your calculator will actually probably has still stored them in there. And then you can go and find what your A and B are. Okay, now I will check one thing. So I'm just going to pause the video for a moment because this is a bit confusing. 1 second. Okay, so I've gone back to my scientific calculator from before, and we're in that shift stat 2 variable statistics, and we're looking at all these statistics. Now I've scrolled down to A and B. Now notice that my A, negative 865.62, actually is B, and my B, which is 11,631.46, is actually my A. So this is the weird part. If you have a green Texas Instruments calculator, it's because it's in America, they actually write their A and B as opposite. So they actually, when they write A, for us, that actually means B. And when they write B, that actually means A. So if you have a green calculator, you just have to remember that if you're using your calculator to find A and B, you just have to flip them. So that's not actually A, that's B, and that's not actually B, that's A. If you're using one of the grey Casio calculators, the A and B is already correct, so you don't have to change anything. So you just have to remember that. Okay, so all we do is we've calculated our A and B. So my A is actually this one. My B is actually negative 865.62. We write those values down, and then we sub them into the equation. So my A was here, so 11,631.46. My B, negative 865. So you see how it says in the formula plus B. Well, if you're adding negative 865.62, that's the same as just taking it away. So that's why it doesn't say plus minus. I just written subtract 865.62 lots of X. And then the last step is we need to go and interpret it properly by putting the correct words in. So remember, our X-axis is years because the age because the age predicts the price. So age goes where X is and price is where Y is. Okay, perfect. So that's how we do those questions. Now here's the example I was talking about, which is predicting. So once we have this equation, we can predict the price of any dirt bike if we know its age, okay? So this example uses the previous one. So let's predict the cost of a dirt bike that's 6 years old. So we're going to write price equals, and we use our formula from before. So y equals, or price equals 11,631.46, subtract 865.62 times age. And then we actually go and substitute in the value for age because we know it's 6. So we go put 6 in there, and then we put all that in our calculator and it gives us a value. And we write a therefore statement. So therefore, it can be predicted that a second-hand dirt bike that is 6 years old would approximately cost 6,437.74. This is a prediction. We don't know this for sure, but it's better than having no idea what a dirt bike would cost us. So one thing on predicting is interpolation and extrapolation. So when we're using a regression line to make predictions, we must be aware that the equation found applies only to the range of data values used to derive the equation. So when we're predicting within the range, this is called interpolation, and when we're predicting outside the range, it's called extrapolation. The easiest way to show you this is just to go back to this table. So this table has dirt bikes, secondhand dirt bikes ranging from 1 year old all the way through to 11-year-old dirt bikes. So before, when we predicted a 6-year-old dirt bike, we would probably get a pretty accurate answer. And the reason for that is because 6 years old is sort of right in the middle of the sort of youngest, like the newest dirt bike, the oldest dirt bike. 6 is fine. If we predicted the age of, say, a 15-year-old dirt bike, that is when we can start to have problems with our formula, because 15 is not considered in any here. 15 is actually 4 years older than the oldest dirt bike. So we're probably likely to get an incorrect or less accurate answer. And that is an example of extrapolation. It's when you go outside the range of the data. Okay, I hope that makes sense. If you want to read a bit more, you can read on page 75.